In this lecture, we're going to revisit the question of what state a BEC is in. We first answered this by considering two BECs being dropped together. If we have them coming from different traps and we bring them together, then their interference pattern should tell us, because we decided that the expectation value of the density, if they were coherent states, would give us lovely interference fringes, and if they were in number states, then we just get a big washed out mess. And then we went and tested that. We used the Bose-Hubbard model. The Bose-Hubbard model is an approximate model for a large number of atoms in a lattice. And if we have the atoms in a lattice, then really only the bottom levels in the lattice are relevant, in which case we can get an approximate model just like this, with that Hamiltonian. And that has two main ground states. The ground state where it's a superfluid state, that's where the nonlinear terms are small compared to the coupling terms. And you do that, by the way, by not having lattice too deep, because that lets the wave functions overlap a little bit more. And the other way is where the nonlinear terms are really strong compared to the coupling terms, and you do that by making it very deep, in which case you're compressing the wave functions and making that density high, and you're also restricting J at the same time. And what we saw was that when we have a lattice, we get interference fringes. When we turn the lattice really deep into the mod insulator regime adiabatically, we tend to get the mod insulator. And that's not just losing phase, so experimentally we could always come back to the superfluid regime and see it. So we're seeing, yes, we really do get interference fringes when we've got superfluid regime, and we really don't have interference fringes when we have the mod insulator regime. And this is all very exciting and interesting. It led us to believe that when we have a BEC just sitting there, not, for example, crushed into a trap, then it must be in some kind of coherent state. We can see from this expression here that the absolute phase of the coherent states alpha 1 and alpha 2 doesn't affect our interference pattern. So if we change both of alpha 1 and alpha 2 the same way by the same amount of phase, of course we get exactly the same interference pattern on average. And indeed, if we're loading our atoms into independent traps, there's no real way to control that phase. We might be able to control, in some sense, the number of atoms that are in that trap, but the phase of the atoms in that trap is out of our control. So we'd expect that if we were to load the trap, we would actually end up loading it with a mixture of coherent states with different absolute phases. But in fact, there's no particular reason to expect that we'd be able to control the relative phases either. If we have two completely independent traps, then whatever coherent state is produced will have a random phase, one would imagine. And so therefore, we might really expect that the state will be a mixture of all phases. Now, what would we expect that to produce? We'd expect that to produce an interference pattern each time, because that's how a mixture works. You'll get, on each particular occasion, a randomly chosen pair of phases for your two coherent states, and then you'll do the experiment, and the experiment will give you an interference pattern no matter what those two phases are, but depending on the choice of the two phases, the fringes will be in different positions. So that's what we'd expect to see if we put that state on a detector. Good. Okay, and now for a little piece of algebraic magic. So all I've done there is expand out my four coherent states into number states. And of course I get a large number of sums. What I'm going to do now is one of the very few tricks we ever use is we reorder the sums. And from there it should be fairly obvious why we did that. These integrals here are in fact known. Because those n's are integers, those integrals are just delta functions, Kronecker delta functions for n1 and n3 for this one, and n2 and n4 for that one. And that lets us get rid of two of these sums. And therein lies the surprising result. This is just some function of n1 and n2. And what we have here are no off-diagonal terms. So in other words, this is a mixture of number states. This distribution here is called a Poissonian distribution. But the key fact here is that this mixture of coherent states with unknown phase is precisely the same thing as a mixture of number states with unknown number. Now what would we have expected if we'd taken a pair of number states and dropped them on our detector? We would have expected to see no fringes whatsoever. But if the two density matrices are exactly identical, then they must give exactly the same answers for all possible experiments. So what's the resolution here? How can a mixture of coherent states with different phases be exactly the same thing as a mixture of number states? Where's the error in our thinking?